Hi, and welcome to another AFM tutorial in the Critical Appraisal series, where we hope to help you learn the basics and how to understand and navigate the medical literature. In this tutorial, we will focus on statistics that test the confidence of results and aid in reality testing. In other words, statistics that help us determine how close a result is to the true population value. We will look at confidence intervals and p-values. Because these are two very important topics, we will do these in two parts to give each topic the attention it deserves. So let's get started with part 1, confidence intervals. Confidence intervals are an important concept to understand in the medical literature, and an increasing number of papers are using them. At least 3/4 of papers use confidence intervals, so understanding them are fundamental to understanding the medical literature. To begin with, we first need to understand a few basic concepts. When we perform studies on a population, it would be impossible to include the entire population, which could number in the millions or billions, into the study. We therefore use what is called a sample, or a small portion of that population, to represent the entire population. And because we use a sample, we need to understand whether the results from the sample are a true reflection of the population at large. We use confidence intervals to help us test our results against reality and determine how confident we are in those results. The good news is that we don't have to calculate the confidence interval. Statisticians do that for us. Confidence intervals give us a range, and it tells us that within this range the true population value lies. In other words, if we had the data for the whole population and not just the sample, the true value, and not just the sample value, would lie in between this range. Now, confidence intervals can be a tricky concept to understand, but it is definitely worth persevering to grasp the concept. Let's make it easier to understand with an example. Let's use the fictional drug X as an example. You do a study to find out how much drug X brings down the blood sugar in diabetic patients. You only have access to diabetic patients who take drug X in your own hospital to do the study on. This is your sample. But remember that the whole population is actually all diabetics who take drug X in the world. In your sample, you found that drug X lowered the blood sugar by an average of 5 millimoles per liter. But is this true of the whole population of diabetics who take drug X? Statisticians calculate that they are 95% confident that the blood sugar would be lowered by between 2 and 8 millimoles per liter if the entire population was studied. This is the confidence interval. Let's see how it is written out in a study. So the average value that drug X lowered blood sugar in your sample was 5. The statisticians calculate a 95% confidence interval of 2 to 8. This is usually written out in a journal article or study paper like this: 5 millimoles per liter, open brackets, 95%, and CI for confidence interval, and then the range, 2 to 8, and close brackets. Okay, so we now know what a confidence interval is. But what do confidence intervals do, and why do we need them? Confidence intervals give us more information than simply stating a value in a study. It gives us information as to how true that value may be. In our example of the fictional drug X, our study produced a value of 5 with a 95% confidence interval of 2 to 8. What if the confidence interval of a similar drug, we will call drug Y, was 0 to 20 with the same value of 5 millimoles per liter? Which result would you have more faith or confidence in? Both drugs have a value of 5, but the range of the 95% confidence interval is much broader or bigger in drug Y with 0 to 20 than in drug X with 2 to 8. Let's have a closer look at broad and narrow confidence intervals. Studies with a small sample size usually produce a wider confidence interval. Studies with a large sample size usually produce a narrower confidence interval. Larger sample size gives a more accurate picture of the whole population. In this graph, various sample sizes are shown with their respective confidence intervals of the same study. N equals 2 is a common way of showing sample size. For example, here the sample size is 10, here it is 50, and here it is 500. The purple dots represent data points in the study, and the red lines indicate the 95% confidence interval. You can see that as the sample size grows larger, the confidence interval grows narrower. So from this, we can see that the larger the sample size, the narrower the confidence interval. And the narrower the confidence interval, the more precise the results. So coming back to our example of drugs X and Y, if the confidence interval has a wide range, it is more difficult for us to understand where the true value lies. For drug Y, it can be anywhere from 0 to 20. That means we have much less confidence in where the true value actually lies. So the narrower the range of the confidence interval, the better. You will sometimes see confidence intervals that include 0 in some papers. For example, a 95% confidence interval of 0 to 12 or of -3 to 15. When these values deal with direct measurements such as blood sugar or heart rate, it implies that there's a chance that the true value is 0, which could mean that there was no treatment effect. Confidence intervals that include 0 in this way are not statistically significant and make us less confident of the results. We should regard these values with caution. For values that deal with indirect measurements such as risk and odds ratios, which we will get later in the critical appraisal series, these confidence intervals should not include 1 for the same reason. They imply that there was no treatment effect. And again, coming back to our examples of drugs X and Y, drug Y includes 0, as the range of the confidence interval is 0 to 20. This means that the true value could be 0, which means that drug Y did not lower the blood sugar at all. In other words, it didn't work. By tradition, most confidence intervals are set at 95%, but it is possible to get confidence intervals of 90 or even 99%. The lower the percentage confidence interval, like 90 as opposed to 95%, the less sure we are of capturing the true average of the population data. I won't get into specifics as this gets very complicated, so leave it at most confidence intervals are set at 95%, but other values are still possible. Confidence intervals are sometimes used in graphs called forest plots or blobograms. These graphs combine data from different studies using a statistical method called meta-analysis and show it graphically. You can see our old friends here, drugs X and Y, with some newcomers, drugs A, B, and C. The confidence interval of drug X is the narrowest, with the confidence intervals of drugs Y and B both being very broad. The confidence intervals of drugs Y and drug C both include 0. You can also see something here that looks like a diamond. This is the combined estimate, and it shows the combined estimate of all the confidence intervals included in the study. As you can see, forest plots plot the confidence intervals of many different studies and let us analyze them together. This kind of graph can often be found in a systematic review. You can find more information on systematic reviews on AFEM's Level of Evidence Critical Appraisal tutorial. Okay, let's sum up what we have learned about confidence intervals. Confidence intervals show us how sure we are that the true population value lies within the given interval. Confidence intervals are an important quality indicator in articles. Articles that include confidence intervals give more information and are more open to critical appraisal. This tends to show a study that is of better quality than articles that don't include or obscure this information. Narrow confidence intervals imply a large sample size with better precision. Confidence intervals that include 0 in direct measurements or 1 in indirect measurements are not statistically significant because they imply that the true value could show no treatment effect. Great work on completing the confidence interval section. Join me for part 2 of statistics that test reality and confidence, where we will be tackling p-values. Thank you so much for tuning in to another AFM Critical Appraisal tutorial. I hope that you enjoy this tutorial. For more great AFM videos and resources, please go to afm.africa/resources. Thanks again.